No. So looking forward and again continue with the important facts and features to take note about support vector machines, which is part of our important clarification series in our weekly presentation. So today we are going to look into a few of the very important remaining parts. Especially, we clarified that support vector machine is very, very powerful with several unique features, especially when you are dealing with data with huge dimension. This is when the number of features are really very huge. And often than not, the number of features, the number of samples cannot be increased randomly. So you always have situation whereby number of features are more than what we expect compared to the available number of samples. And this is a very common problem that often leads to what we call cost of dimensionality. That is, as the number of features increases, then the number of samples needed to achieve reasonable results increases exponentially. And any problem that grows exponentially, it's a very, very super difficult problem to address. And this is one of the very strong points of support vector machine, that we say that it doesn't suffer from cost of dimensionality, which is one of the very, very serious problems common to most of the machine learning algorithm. So despite the uniqueness and its capability to deploy what we call the Kernel trick, it also has its own challenge, or even challenges. So one of the challenges of support vector machine is that it doesn't have direct multi-class solution. You cannot use it directly for multi-class problem. When you have more than two classes, it only works for binary classification. When you have two classes, yes or no. When you have three classes, A plus, B plus, C plus, it cannot solve it directly. So today we are going to look into how has it been modified to be able to cater for such a unique need of the community, because you cannot always guarantee that you are going to have a two-class problem. So sometimes people need to deal with multi-class problem, which is normal and sometimes even common. So how do we solve that in support vector using support vector machine? So that's why we have today, what about multi-class support vector machine? So you say, unfortunately, there is no definitive multi-class SVM formulation, because as we have described, it only works on the principle of seeking for an hyperplane between two classes. So you can only draw an hyperplane between two classes. You cannot draw it among three classes. So we have to have a way to do that. So in practice, we have to obtain a multi-class support vector machine by combining multiple two classes SVMs. So the only way to bypass this problem, to resolve this, is to train multiple two-class SVMs. So it still has to be two-class SVMs. But we're now training in multiple ways, multiple times, combine them together. So in doing this, there are two ways of doing this. Number one is the one we call one versus others, because we have to train pairwise. One versus others. That is, here you learn an SVM for each class versus the others. So, and then apply each support vector machine already trained to test example and assign it to the class of the SVM that return the highest decision value. So in this case, if I have like A, B, C, D, these are four classes, class A, class B, class C, class D, what I need to do is to train, the first one will be train A against B, C, D, one versus others. So I'm going to consider all these like one class. You see, we consider all these three classes, we make them to be like one class. We can label them to be All of them, this is class A, and these are all other class combined together as one. So we can separate A from it. So this is what we call one versus others. So the second way of dealing with it is the one we call one versus one. Here you are going to train SVM for each pair of classes. See? So then each learn SVM vote for a class to assign to the test example now. So thereafter, then each of the SVM will now select, okay, for every sample, which class should we assign it to? So for the same example of ABCD, this is how we are going to make it. So since we have 4 classes, ABCD, we're going to train class AB. You try to separate them, A and B. You train another SVM, AC. You train another SVM, AD. Pairwise. AB, AC, AD. Then you have to train another one with BC. Then you train another one with BD. And then you're going to train another one with CD. So you have to have different two combinations of 2-class SVM repeatedly trained, and then the final decision will be made by voting among them to which class each of the samples we have to belong to. So diagrammatically, this is the first one versus others, how it works. So let's say we have these are classes we have. We have normal class, abnormal class, broad, high, medium, and low. 1, 2, 3, 4, 5, 6. We have 6 classes. For one versus others, so we are going to pick normal. We are going to separate it from others. You can see here, it's okay, one against all. So this will be considered positive class, while all the other one will be considered negative. You see? So a labeling of the entire system, all these abnormal class, broad, high, medium, will all be considered as negative class. So once we are done, then we again continue with the separation. Then we pick another one again, make it positive against all others. You see, you have high, medium, and then low as others. Then you move on, you keep doing that until they are all fully separated. So this is how one versus others work in a support vector machine. The second way is the one versus one, in which case you have to train for every pair, you have to train different support vector machine for them. So you can see here, you're going to have, this is class C2 and C1. So you have to train a kind of system, a hyperplane. You have to train hyperplane to separate them, C1 from C2. Then you train another one for C1 and C3. See, C1 and C3. Another one, you have to train it. Then you have another one for C2 and C3. So by so doing, you're going to have multiple 2-class SVM trained in many ways, and then later, the solution will be gotten from all of them by way of selecting the one with the highest vote. So these are the 2 ways by which support vector machine solve the problem of multi-class problems. So it doesn't do it directly based on its principle that it can only separate 2 classes. That is the basis. So, and that is one of the weakness. However, the people try to bypass it. And also generally, so when we, maybe earlier on in our weekly engagement, we also classify. Sometimes the more the number of classes actually, the more challenging for you to get very high accuracy. So that is why it's even sometimes preferable that you try to bring down the number of your classes so that you can be able to achieve very high predictive power. Because as the number of classes are increased, there are also challenges for the algorithms, even though they have that capability from onset. So the idea of training pairwise is something that is actually also highly encouraged. Now, other pros, the pros of support vector machine, the advantages, the positive side of it include that it works really well with clear margins of separation. We've demonstrated that in our previous videos on this. It's also effective in high dimensional space. We said the secret behind it is that once it's trained, it will represent the entire data by the few support vectors. Support vector. Once the training is done and support vectors are identified, when you go for the testing set, you don't need the entire samples from training. Just the representative samples that are referred to as support vector, they are enough to provide whatever we need to move on with our testing set prediction. So which is a very unique capability of support vector machine. And that's why it's very effective when you have high dimensional data set. And also when your samples are very low, we've noticed this, it is very effective. If I also say it is effective in cases where number of dimensions is greater than the number of samples, yeah. See, in very rare cases where the number of dimension, by number of dimension here, we mean the number of features. Number of features. When the number of features is greater than number of samples. This is actually it's an abnormality. See, when you have like, let's say X1, X2, X3, these are features, up to maybe X11, or let's say 45. We have some problem with so many features. You have 45 features. However, the number of samples, sample 1, 2, up to like maybe 40. You can see the number of features is even more than the number of samples. This is a classical case of super cost of dimensionality problem. Because once you increase the number of features by just one, let's say we have X1 only, we are in need of 10 raised to power 1, for example, samples to make a reasonable prediction or reasonable resolution. However, when I increase it from X1 to X2, I'm expected to have not just 10 plus 1 samples, but I need 10 raised to power 2 samples, which is 100. So if I increase it to 3, I need 10 raised to power 3 samples to be able to make reasonable stuff. But now imagine somebody is having X45. It means I'm supposed to have 10 raised to power 45 samples. However, the client only provided us with 40. You see, which is not even enough for if I have two features. Because if I have 2 features, I'm expected to have like 10 raised to power 2. But here I'm having only 40 for 45 features. As serious as it is, support vector machine has often demonstrated that the capability to still deal with it actually and achieve reasonable results, outcome. So from experience, we have not seen any other machine learning algorithm that behave in this very unique way, actually. So it's a very unique characteristics of support vector machine. So usually you have so many features, but the number of samples, they are very limited because you can easily create features. If from one feature, you can combine them to make another features. So features can easily be created from your samples. However, getting number of samples is not something you can just create. So it just have to be available, especially in material science and engineering. It's very challenging to get more samples. So support vector machine is usually one of the machine learning algorithm to go for in such situations. You say it uses a subset of training point in the decision function, which we call support vector. So it is also memory efficient. So since once you train support vector machine, even if you have 1 million samples during training, it only selects the support vectors, which are the subset of the training point that support the decision function, the one that are sticking to the margin point. So when you train with 1 million samples, the moment you finish with the training, let's say your support vector machine, it got in support maybe 10 support vector from one side, another 10 from another side. So it will use these 20 samples to represent the entire 1 million. So the other 1 million samples, except these 20, so that means all others will be discarded. They can be deleted from the memory. It will be dealing with the testing set using only 20 samples retained from all these. Just imagine the kind of memory efficiency we are talking about. So irrespective of the size of your data set, once the training is done and support vectors are identified, then the system can do away with all the samples except those support vectors. And those are the support vectors, those are the samples that will be taken to the next stage in the testing side. And that is why the testing for support vector machine is usually very fast, because it's not carrying the entire training samples like others we do. No, it only needs the support vector, and they are usually very few in number. So this is another very unique capability or attribute of support vector machine. So also there are many publicly available support vector package. So you can easily in MATLAB, Python, Weka, whatever environment you want to use, they are readily available. So we can check out this website. We call it www.kernelmachines.org. It's all about support vector machine. Because it uses kernel trick to solve very challenging problems. Then it is kernel-based framework is very powerful and then flexible. So among the unique capability of support vector machine is the kernel trick. So once you are able to push to another dimension, everybody has a prize. So you keep pushing. If it's not separable at the lower dimension, you push it to second dimension. If it's not yet doing, keep pushing it until it definitely will get the problem solved. So this is a very super capability of support vector machine, the kernel-based framework. So we said support vector machine work very well in practice, even with very small training sample size. These are things we have demonstrated. So even with very simple few training samples, up to 16, we've worked on 16 before. So where all the algorithm failed woefully. So if it's an algorithm, you cannot even think of running experiment with not up to 100 samples, not to talk of 16. A support vector machine has often demonstrated this unique capability. So whenever you are faced with few data points or high dimensional data where your features are almost too much compared to the samples, then it's good to always quickly have a look at support vector machine and see how far it can go. However, again, always remember, we are not saying support vector machine is the best algorithm. We're only describing some of the unique feature of it, and we have demonstrated and deployed them in our applications with often very unique outcome. However, the principle of let the data speak does not allow us to say that any algorithm is better than all. There's no algorithm that is better in all situations. We have situations whereby we have to use other algorithms to solve problems, where support vector machine was not getting what we wanted. So it depends on the nature of the data set, but from our majority of our experience has been able to confirm some of these unique attributes of support vector machine. The cons, everything that has an advantage also has its own challenges. So some of the disadvantages or challenges of support vector machine include it doesn't perform well when we have large data set because the required training time is higher. Yeah, if your data is really huge, so because the training is not just it's not a simple training. It's involved having to do a lot of quadratic optimization procedure are involved in support vector machine. So which we add to computational complexity. So when you have a system, especially if there's a real-time system whereby you have to train and retrain. You have to train and retrain while new data are coming in, and you want your result in real time. support vector machine might not be an option for you. There was a time we faced a kind of project like that. We have what we call extreme learning machine, ELM, and support vector machine. SVM was getting, I think, 100% in testing, while ELM was getting like 97, 98%, 99% in testing. So we had to go for ELM because in that problem, the recommendation was that if you are going to have your problem solved in batches, not real time, then you go for support vector machine because it's giving you the best outcome possible. However, if you are going to be using it for real time processing, then you go for ELM because it's extremely very fast in both training and testing. So in that case, sometimes you have to make such provision, and that's why you always run more than one algorithm. Even if the two of them are performing, you have to look at the reality of what you want to use it for. If it is real-time deployment, where they're going to be retraining and retraining, support vector machine takes time in training time for only the training. But once the training is done and you have gotten the support vector, the testing doesn't take time. So we want us to get down very clear. But in an online system whereby new sample will be coming in, retraining will be done, then you cannot rely on support vector machine to quickly retrain and get you the result. Because it takes some time because of the nature of the formulation of support vector machine. So also even conversion, whenever you want to use the kernel trick, for example, look at it here, during the training time, you must compute matrix of kernel value for every pair of examples. Because if you want to use any kernel function, so it means every sample must first of all be converted using the kernel value. So imagine you are having 2-3 million or more samples for training. So even the conversion alone, calculating the kernel for each sample before you start your training proper is going to add a lot of computational complexity to the system. So that is why for real-time application, it might not be the best thing for you to go for. But if it is something that is batch, whereby you can train and then use it for the system, or if something that needs only one-time training, then subsequently you only need to run the testing as part of it, that is perfectly okay. So you can deploy support vector machine because of the unique capability. So another shortcoming or cons is that there is no direct multi-class SVM. So we just discussed that today. It must combine two class SVMs to solve the problem. So, of course, the computation and then the memory. Yeah, because you have to compute several kernel values, and you have to also the normal sample given to you, they are in memory already, and then you have to compute for every sample, you have to compute the kernel value for them, which is addition to the memory again. But once you are done with the training, this is done in training set, done in training process. But once you are done with the training and support vectors have been detected and correctly identified, then all the samples could be done with, and then you only work with the support vector. In this one, at this point, you can free up the space for subsequent testing. So we said for large scale problem, it can take a very long time for training. That is learning. Pay attention to that. Learning or training takes a very long time for large scale problem. If the data is big, yes, support vector machine might not be a very nice option for you to go for because it takes a lot of time during the training. But once the training is done, then the testing is nothing because support vectors will be the one that will be deployed to do the testing period. We don't need the entire system. So someone has to study the nature of the actual area of application and then advise the client appropriately on the best option to go for. And that is why we always compare different algorithms when you are building machine learning models. So there's no algorithm that will always give you everything you want. So in some, you have this, in the other one, you have that. And that's why we always advocate for the idea of having what we call ensemble. Ensemble is where you're going to combine different methods together so that you can take advantage of different algorithms at different points in time. So we found out that this has always been one of the best way to go. So And then a kind of final brief clarification on why SVM is effective on higher dimensional data, because this is a very big issue in learning or data science. So it always higher dimensional data leads to what you call cost of dimensionality. We have discussed this a lot. We have discussed in our previous videos. We can check it out. Cost of dimensionality. So say the complexity of trained classifier is characterized by the number of support vectors. So this is why SVM is effective on high dimensional data. What is unique in it? Why is he able to perform why other algorithms cannot perform? Especially when you have the example I gave us, you have X1, X2, X3, up to like X45, and then you are only given 40 samples. 40 samples. That is extreme high dimensional data. So most likely will lead to cost of dimensionality for an average algorithm. A support vector machine is often able to outperform these kind of challenges. Because of this, one, that the complexity of the trained classifier is characterized by the number of support vectors rather than the dimensionality of the data. So when the training is done and we identify support vectors, we're practically going to ignore the actual training data irrespective of the dimension. The identified support vectors will be what we are going to use for the next stage. So the support vectors are the essential or critical training examples that lie closest to the decision boundary. So again, also if all other training examples are removed and the training is repeated, the same separating hyperplane will be found. That's another unique possibility. Even if you decide to retrain the system using only the support vectors, you still arrive at the same decision boundary that you achieve using the entire training set. So therefore, we say the number of support vectors found can be used to compute an upper bound on the expected error rate of SVM classifier, which is independent of the data dimensionality. Thus, an SVM with a small number of support vectors can have good generalization, even when the dimension of the data is really very high. So this is the secret behind SVM having huge, good performance and making it very effective on high dimensional data. Or somebody may ask, this is the reason why support vector machine does not suffer from cost of dimensionality. Cost of dimensionality. So by far, the two unique capability we can summarize is the use of support vectors that made it to bypass this cost of dimensionality, and also the kernel trick that if something is not separable at a particular level, at a particular feature space, it pushes it to another higher space, keep pushing it to another space until it gets separatable. And I give a real life example that even in real life, if you have to separate people who you want to identify who can run, who cannot run, you have to subject them to unique tasks. Let them run a particular marathon and see who can come back or who cannot come back within a time. So by so doing, everybody at every point in time will drop along the way so that you'll be able to know who can really match up with the requirement you are looking for. And that is exactly what support vector machine does with the kernel trick. It keeps pushing up the samples until they get to a particular feature space where they are going to become separable from only one dimensional to two dimensional to three dimensional as much as possible until they get separable using the appropriate kernel function. So which kernel function is better? Again, it has to depend on the principle of let the data speak. Depend on the data you are dealing with the appropriate data. Want to believe support vector machine can solve your problem effectively and with interesting outcomes, better than some of the available systems. But however, you always encourage to check out others because you cannot really tell how the particular data you are having is going to speak. So always let the data speak by checking other classification as the case may be. Check other classification algorithm or other predictive algorithms before you finally stick to the one you want to use. I think this is where we get to have it for the day. So before then, we just list a couple of applications of SVM. The SVM has been used successfully in many real-world problems. It's not limited to text and hypertext categorization, image classification, bioinformatics, handwritten character recognition. This is one of the areas where we've gotten 100% testing accuracy in the past. So it's not something easy to get, but with very huge data sets, sometimes you can achieve that. And also for the application, medical and biomedical application areas, it has always proven to be very effective in solving the unique problem. So this is what we're going to have for support vector machine for now. So if we have any question, we are going to take a couple of questions, and then we're going to give time for us to ask questions. These are some key points. So we're going to share also the slide with us to go over at our own time. So we are encouraged to use optimization to find the solution. That is the hyperplane. Optimization is very important in anything you do. No matter how unique an algorithm is, you have to check the optimization. Check the parameter that's going to work for it, the hyperparameter that work for it. Seek large margin, use the Kane trick. Yeah. So, and then use appropriate the normal procedure that we have discussed so far on how you can ensure that you train appropriately, which is using the hyperparameter optimization. Very important. So that you're able to do the right Kane. Is it polynomial that work for you? Is it Gaussian, or which one that work for you? What is the value of C that's going to work for you? Without hyperparameter optimization, then we are not being fair to the algorithm, and that is also general to all the other algorithms that we use in machine learning. So let's make sure we carry out the number of procedures which we already also discussed with ourselves to make sure that we are able to achieve the best possible outcome for whichever algorithm that we are using. Finally, always remember that let the data speak. So no algorithm is always better. So you have to investigate and check out the one that works for the present data set that you are facing. Thank you very much.